Okay, so thank you so much for being here. I'm Cheryl Clarkson, and I work in the George Washington University at the Nanofabrication and Imaging Center. And today I'm going to be talking about some key aspects for the CLEM microscopy from a practical perspective. Sorry. So as you can see here in the left, it's like we have so many different modalities from the light microscopy to the electron microscopy that we can combine to try to get the best aspects of or the best results from our experiments. But the first thing that is like when we are planning to do a CLEM is like we need to be very clear about your question. It's like if you can resolve these kind of CLEM questions, it's better to use an easier methods. But sometimes it's like you really need to use CLEM. And this is one of our cases. This is my particular project where I'm creating, as you can see here in A, like a lesion in the CNS in the brain of a mouse. And you can see here that I'm creating a neuroinflammatory microenvironment that at the end is resulting in these cells that you can see here in red, that they are re-expressing a transcription factor that normally is not expressed during the adulthood. So at that moment, it's like this is a very surprising finding, and we thought, we can know which kind of cells are this one. And before to go in CLEM, for sure, what we did is like we went to a very easier methods as like is the colocalization with different markers. Are these one neurons? So we use markers for neurons, for astrocytes, for microglia, macrophages, pericytes, astrocytes, endothelial cells, everything that you can imagine. And what we can found is like it was we have colocalization with microglia, macrophagy, but was not really super specific. So then we try to go in depth, and it's like we use pro-inflammatory, anti-inflammatory, and it's still not super specific. So what we did at that moment is like we need to know, but we found that they are microglia, macrophagy. So at that moment, our question is, so are these microglia and macrophagy a little bit different from the other ones? So that is the moment that we need to see the ultrastructure of these cells. Are they phagocytating more? They have different kind of inclusions. They have different type of mitochondria. What is so special in these particular microglial cells that they are re-expressing this transcription factor? So at this moment, we decided to run CLEM. And we decided to run CLEM because if you can see here, we are combining the positive vibes, the positive results from the light microscopy, like we have the entire molecular profile of these cells because we can use different antibodies, different reporters. We can do a lot of combination, but also even using super resolution in the light microscopy is not enough to resolve little questions like are the cristae of the mitochondria in the good shape or whatever. So that is the moment that we are also using the electron microscopy to gain in the real high resolution. And this is awesome because you can combine both modalities, the positive stuff of both modalities, but also you are adding a lot of little steps in the protocol for the sample preparation of this, and that's why I want to highlight today, okay? So I'm going to be showing what we are using here in the center as a regular protocol. So the idea is like we try different stuff and we are able to tune up with every kind of tissue, but normally we are starting with a perfusion of the alive animal or with chemical fixation in the case of the cell culture. Then we are doing the immunofluorescence if we need. If we have a reporter, we don't. And then we are performing the light microscopy imaging in a high resolution. And then we are post-fixating the same tissue for EA, where we can add the glutaraldehyde to pump or to keep the ultrastructural for this tissue. Then we are running the sample preparation for EM with the heavy metal protocol. Then we are passing to the EM imaging for 2D or 3D. We can use both, and they can give it to you different kind of results, and at the end we need to finish with imaging analysis. So we are going to start with the sample preparation for CLEM, and the first thing is like plan your experiment. It's going to be a tissue or it's going to be a cell culture. And this is very important because if it's going to be a cell culture, you have to plan before start experiments that it's better to use, as you can see here in the left, These are grids, they are microwells, bottom glass dishes, that they have these fiducial points that you can sit your cells in there, and they are going to be very helpful to see if we have our target cell in BA. So it's like we can go in there, and also we can have the same fiducial point in the CM. So it's always an easier way. We have different kind of commercially available stuff. You have different glass thickness depending about what you want to do. And this is very important, mostly if you are going to be doing inverted, if you have an inverted scope, so you need to be using these glass bottom dishes. So the idea is like you plan ahead, because once you put in on your cells in these particular glass slides, they need to be adequate to do the imaging in there. So then the other part that is really important is like how you are going to plan your sectioning, because you have to remember the same section that you are going to be doing during the light microscopy imaging, the same section that you are going to be running the immunofluorescence needs to be processed at the end for the EM. So in these cases, you have to compromise a little bit about the thickness, because the EM is very cool between 300 and 500 microns. That is very thick and sturdy, that you can move very easily. But for the light microscopy, the immunofluorescence, they don't like too much such a thick sections, and we cannot use clarity, we cannot use BABB, because at the end we are going to be using EM. So we compromise a little bit, and we are cutting around 150 microns. And this is very important. We can just use vibratome, nothing like a cryostat, no microtome, you know, because we are going to be creating ice crystals that at the end, everything is going to be seen in the EM sample prep, in the EM imaging. So the idea is like you are very, very, very careful in your immunofluorescence preparation also, to keep the ultrastructure that is going to be seen at the end of the EM, because you can be performing for 1 week an entire experiment, and at the end you smash the ultrastructure. So this is very important to have or to take into consideration before starting. So after we have the animal or the tissue fixated, and after that section, if it's a tissue, we are going to start with the fluorescence. So if we are going to have a tag molecule, a reporter, that is all the time much better. And this is very good if you can have an animal or a cell line that is having an internal reporter. It's much easier, because you are going to remove all the steps from the immunofluorescence. That is like if you are going to be adding twin, triton, or whatever, it's going to start to break your membranes, and everything is going to be seen in the EM level. The reality is like the reporters are awesome, and I'm going to show you some examples with the reporter, but the majority of the time, like you need fiducial points, you need to like label, by example, in the CNS, like the blood vessels, to have some areas to you be able to localize your structure. So at the end, you finish using immunofluorescence. So performing immunofluorescence. So the idea is like you are as gentle as you can with your triton or your twin, whatever you are using. And also the timing, because like we are cutting 150, so it's a good idea as a tip to increase the times of incubation for the primary and for the secondary antibody. So that is my advice. Then we are going to run the light microscopy imaging. So what is the important? Our region of interest, if we are going to be running a large area, if it's going to be 2D, 3D, in vivo, confocal, or super resolution imaging. So this is the same example that I was talking at the beginning with the cells that they are expressing this transcription factor. So you can see here in A that I have a very large area from the CNS, from the cortex of this animal. But at the end here, that you can see here highlighting in this shadow, I have my lesion. So you can see very lightly here my lesion track, and here in this rectangle, I have my region of interest. So here we have a little bit of like a high magnification. And if you can see here, what we choose like as an area, because I'm targeting these red cells, is like I have something that is a little bit different, because when you have all this ocean of different type of cells, and now in the light microscopy, you are like you are feeling very confident that you are going to see them, but when you are going to the EM, it's going to be very challenging. So my advice is all the time, as you can see here, in this one that is called GFAP snail, you see that this astrocyte is an astrocyte labeling is going with this cell that is very, very flat and that is embracing or enwrapping these blood vessels that you can see here highlighted in blue. So I have like these little fiducial points. So I have very good because I have 1, 2, 3, 4 blood vessels. I have these very flat astrocytes that is just in the middle of my lesion tract. So I know that it's going to be easier for me to track in the EM. So my advice, because you can do a very large area as an overview in the light microscopy, but then you need to go to your region of interest to run your high resolution imaging. So at that moment, in the light microscopy is easy peasy, but in the EM level is very, very, very challenging. You can see here I did after we ran this is done in the Leica in the 2-photon SPA. You can see here I did a really fast like a surface model in the IMARIS with this data just to try to have in mind a 3D of my volume that I did for the light microscopy. So all the time you have to think about fiducial points, what I'm going to be able to recognize that is different enough, because this is tissue. It's not like the cell culture that I have my BA. This one is like you are going to be totally lost. So after I run my light microscopy, I need to pass to the EM sample prep. So we have to post-fixate our tissue or our cell cultures, and this is the moment before we cannot put it on the glutaraldehyde, because the majority of the antibodies, they really enter, and you have a lot of autofluorescence with the glutaraldehyde. So we are not using the glutaraldehyde until we finish the light microscopy approach. So at that moment, you have to be sure about what you acquire already for the light microscopy. And you can see here, we have tissue. We are post-fixating for 24 hours, adding this glutaraldehyde. And for the cell culture, we are using just 1 hour and a little bit less of the PFA, but a similar amount of the glutaraldehyde. After we are done with this part, we are going to start with the sample preparation. And now we are using the Daring 2010 protocol, the heavy metal protocol that the majority of the people that is using volumetric EM, we are using as in daily basis. This is something very important because some people, they don't have, by example, SEM like we have, and they have TM. This is something that also you can use for the TM samples without any problem. And the only thing is like sometimes is overstaining the membranes, because that is the idea, to pump our sample prep with a lot of heavy metals that is going to give it to us a lot of signal that is going to be easier for our imaging. But sometimes if your target is something like is membrane-ish, probably this is not the best approach. So you need to fine-tune this protocol. You can decrease the potassium ferrocyanate, you can decrease a little bit the TCH, you can play a little bit until you found the perfect condition in a troubleshooting tissue. Don't use it for testing in your CLEM tissue that you already imagine for the light microscopy, testing before, but it's something that is a very good start. We have been using for kidney, we have been using for bones, we have been using for CNS, that is the easiest, spinal cord, brain, and it's the whole time a very useful technique that is very easy to approach. The only thing is like you need to have into consideration that it's going to take a little bit longer, between 1 to 2 days for cell cultures, and between 5 to 6 days if you don't have a microwave for the tissue. And after we have all this part done, so I'm just going to be showing to you how we mount these sections, because I'm going to be showing to all of you guys some examples from our past workshop that we are doing CLEM. And this is the first time that we were doing CLEM with volume scope. That is a little bit challenging because I don't know if you have some experience with volume scope, but you are entering blind and normally you have to cut blind. But the idea to run CLEM is like you have the light microscopy, and immediately you need to start with the EM because you want to correlate what you acquire in the light microscopy with what you have from your EM. So here, you can see here, after we have our tissue, I have the brain embedded in the Clark films, and after that, I'm just trimming my tissue, and we have these very particular stabs that they have for volumeoscope, that they have this little table that you can mount your tissue that needs to be small. And after that, what we are doing for when it's CLEM, I'm just facing the block, and as soon I starting to see the tissue, and this is really easy with the high metal, because as soon you're starting to see black in the plastic, you stop. And then we have to run the sputter coating like a 20 nanometers of gold, in this case, when we are gonna be running volumeoscope. It's a very similar case if we are gonna be running for FIB-SEM. As you can see here, you have different type of stops. For the FIB-SEM, you have more variety, and you just have to put in on 1 or at the most 2 nanometers of platinum palladium. And after that, we are ready with the same sample preparation for running our FIB-SEM as a part of the CLEM. And then we are going to finish with the EM imaging. We have to be sure, sometimes for CLEM, you really don't need the 3D. You can run it with the 2D, or we need the 3D because I want to have the volumetric resolution. Or if I want to be doing with SEM, with TEM, you have the different options, even using the same sample preparation. As you can see here, these are the kind of instruments that we have in our center that we are using as daily basis for this kind of experiments. We have the Teneo that is equipped with the volumeoscope. We have our Helios, where we can perform FIB-SEM when we want to really cut thinner. And then we have our Talos if we want to be super high resolution, that you want to see something membrane-ish or whatever. We have our TEM also. And everything can be used for the CLEM experiments. So that is for like a backscatter, but also we have the ability right now to do in a very fast pace, doing CLEM with the conventional SEM, when you want just to analyze changes in the topography, in the topology, when you have cells like the lymphocyte, that they can be changing their membranes. So we are going to be using similar stuff for the cell culture, the same kind of bottom glass dishes, or also what we are using lately is like we can seed our cells in the silicon wafers. So the silicon wafers, we have here a nanofabrication part of our center. So some of our scientists, he's printed in our silicon wafers some fiducial points. Even he can put in on some fluorescence in there that we can see like A and B, whatever, in fluorescence. So everything, if you are fancy enough, you can get fancier. But if it's not, also you can just scratch your silicon wafer or your glass, and also you can run it. So it's just whatever is make easier your life. So then we are going to be running the chemical fixation as we talked before. We are going to be running our immunofluorescence in our cell culture. And at the end, we are going to finish with the light microscopy imaging. We are going to choose our region of interest. And after that, we are going to start the EM processing with the post-fixation, the staining with the osmium, and running as a regular sample processing with the dehydration, the alcohol dehydration, and then going with the CPD or the HMDS, that right now we are using a little bit more the HMDS to keep the ultrastructure as beautiful as we can. As you can see here, we are mounting the sample, the entire glass. If we have the glass bottom dish, we just need to detach from the corner, and after that, just to transfer to regular stabs with the carbon tape, nothing from the other wall. Very easy or regular sample prep. You just need to be super careful. Then we are putting on, again, a sputter coating, and then we can run, the EM imaging without any problem. So at that moment, we have light microscopy, EM data, and after that, we have to try to combine or to fuse the modalities. And this one is just to show very quickly what we are doing for the backscatter SEM in the cell culture. So we have exactly the same kind of steps until we are going to the post-fixation, because in this case, we are running a dehydration and we are adding the resin to our glass bottom dish. And after that, we can have the cells embedded, as you can see here in the bottom and to the right, embedded in there. And then we are ready after the mounting to go to the FIB-SEM. That is normally what we are performing when we have these cell cultures embedded in plastic. And this is the final way. This is from my own paper. So you have a lot of data, and this is something that is going to come after you have all this gigantic amount of data that you don't know how to show, that you can show very easily, as I'm going to show at the end of the presentation in our software. But the reality is, like, you have to show in a meeting. You can be showing, like, I'm going to be doing the video and everything. But in reality, when you are going to put it on in a paper, the majority of the people doesn't have enough knowledge to understand what is CLEM, how you did this. So this is what I did, and I'm trying that the regular scientists can understand what we have been doing and what we are trying to explain to all the scientific community. So as you can see here, I have the entire, in A, I have the entire steps that I already showed to all of you that we did for the light microscopy in the 2-photon and my surface model. And after that in B, as you can see here, I start in the ultra thin sectioning. And you can see here that as soon in this little blue arrow, as soon as I starting to see the lesion track that is going to start here, I stop it. Because at that moment, I need to start and going to see if I have my region of interest. So I'm not anymore, in this case, I use FIB-SEM. So I didn't want it to go deeper because I have to stop, and after that, just go into the helios and find my region of interest, as you can see here. So I have still the lesion tracking here. And do you remember the very flat cell? So I have it in here. I have my 4 blood vessels in there, and I have at the top here, highlighted with this arrowhead in red, my target cell. So as you can see, I use all my fiducial points, and it's super important. Never believe just in like an accumulation of cells. That is insane, because when you are doing light microscopy, you are acquiring a gigantic volume. And in the EM level, at the beginning, you are really, really lost. So as you can see here, once I found my region of interest, we milled the trench, and well, we did the deposition, milled the trench. And after that, as you can see here in D, I have my phase blocking. I can see my lesion track. I can see in red part of my cell, label it with my transcription factor, and then another astrocyte, that is the flat astrocyte that is running along. And here in E, I was trying to show in some of the ortho slices that I have how I did the volumetric reconstruction. Here I'm showing also the entire EM reconstruction, and here I fuse my light microscopy with my SEM data, my FIB-SEM data, and here I'm trying to do the same. And at the end, I'm just showing at the top how it really looks, the cells, and I'm showing the ultrastructural difference. You can see here that I have even mitochondria, and all this one is after I run, because I run regular immunofluorescence, even with antigen retrieval, so by heat. So you are able, if you are careful enough, even running immunofluorescence with antigen retrieval, that is in theory putting on a lot of stress to your tissue, to your membranes, you can get nice ultrastructure. All these, and even after a lesion, because when you are lesioning a tissue, you are creating a very neuroinflammatory environment that is making your tissue more adhesion, more susceptible to damage. So this is the way that I wanted to show all of you guys, because we are used to be working for people or working with people to try to show them how to do 2D, 3D, and after that, how to fuse. But at the end, all that work needs to be translated in a real image that you can show like by example in a paper. So here I'm just gonna show practical examples. Sorry, I'm just gonna share another part. So let me see this one. Sorry for a moment. Let me go ahead because it disconnects me. Somebody entered to my... Now can you see it? Not yet?
Not yet.
Okay, let me see. Right now, can you see it?
Yes.
Okie dokie. So here, I just want to show, let me go. This is a practical example of what I want to show. So this one is, for me, is the most exciting part because it's what I was thinking that we were not able to perform, that is CLEM with volume scope, because volume scope is the easier way right now that we have for running a large area in the 3D SEM, but it's all the time very challenging because you are entering blind. So I was thinking I have to cut a lot until I'm able, and I'm gonna pass the volume that I already registered for the light microscopy, but we were able to do it, and at the end, it was very easy for saying in some way. So now you can see here, I'm starting to move in the volume, and you can see here how it's showing up. And you can see here at the bottom of this yellow stuff, that is the ortho slicer, how we are having our target cell. And in there, we are having our also SEM data that is coming from the volume scope. We can go. It's lagging a little bit, so I have to, because all this high technology also means a lot of gigabytes of data. So you can see here that we have a very nice reconstruction that after that can be showing to all of you guys that we have our EM data fused with our light microscopy data. So I just want that you are able to see a little bit. So it's very hard, that's what I'm talking about, fiducial points, when you are entering in all these ocean of different type of cells, different type of structures, as you can see here. So let's put in on with this one, and you can see all the time. Okay. Also, we have in here the real EM data. So also we can go here with another ortho slice. Let's put in a little bit of our, and you can starting to see our 3D reconstruction. This is the same cell that you saw it before, but this is the volume scope data. So you can see how it's looking in the SEM level, and we run it with the volume scope. So we can, after that, analyze section by section. We can quantify everything. If you are looking for the changes in the volume of the mitochondria, in the polarization of the mitochondria, if you are looking also for things like a pore membrane, nuclear pore membranes, you can be checking everything with these kind of approaches. It's very easier. Well, for us, it's a little bit easier, but it's like it takes time, but at the end, everything is possible, even running immunos, because in this case also, we run immunos. So if you want, if I have a little bit of time still, I can show another. Let me close this one. I know it's a little bit challenging because I have so many stuff.
Lovely. This lady, she started earlier, it was meant to start at 10.
Okay, can you see this one?
Not yet.
Okay, I'm gonna, I don't know, okay. Let me share this one. Now can you see it?
Yes.
Okie dokie. So what I wanna show here also is like, this one is not moving, sorry. It's not responding. So I'm not gonna be able to show, so sorry about that, but it's okay. So I want trying to show also the 2D because we have some examples with the, so sorry about that. We have some examples with the 2D and with the reporter that I wanted to show you, all of you guys, that also if you don't have a 3D technology, because some people, they don't have volumeoscope, they don't have FIV-SEM, but also if you want to show CLEM, you can still show CLEM just using a 2D SEM. If you have your SEM or your TM, you can do anything like that, okay? So sorry about my little issue.